Hello and welcome to the next lecture on urban economics. It's a great pleasure to welcome Dave Donaldson for this sixth lecture in our series, and he's going to talk about economic geography and path dependence, which is one of the key topics in urban economics and economic geography.
Well, thanks very much for the invitation to be here, and for everyone for making time to tune in. So as Daniel mentioned, I'll be talking about the theme of economic geography and path dependence in the context of urban economics. So, you know, what motivates us here is the kind of astounding extent to which economic activity tends to be clustered over space. And this is an example from the US that I have on the slide there, but you know, examples I'm sure can be found anywhere you look. We're going to talk today kind of a very rough overview of some senses of why that might be the case, why we might see so much clustering, and also try to ask a question of, you know, what are the implications of such clustering? And I want to just flag right off the bat that, you know, I was invited to talk a bit about both the prior work and some recent work that I've been doing myself on this theme. So you're going to see a mix of both of those. But I want to just flag that the very last slide has some mention of some of the best textbooks in this area and monographs that, you know, are exactly the place where I would want to turn if I wanted to dig more into this. Okay, so just a picture that you've probably seen before, but always bears repeating, I think, and viewing again, is a sense of just how clustered are the lights we can see on the face of the Earth if we were to look at them from a space shuttle or a satellite. Zooming in on, say, the US, this is a kind of a picture that exaggerates the contrast between sort of dark space and white space, where there is a lot of light, and we therefore presume, and you know, a lot of evidence suggests there's a lot of economic activity taking place, a lot of concentration of where people live as well, of course. Zooming in a bit more, you could imagine doing the same thing by industry. You know, the previous pictures were obviously for a very broad notion of economic production. And this has been done many times, and these are all almost all American examples. You know, Alfred Marshall, who was one of the first economists to talk about these ideas, gave the example of the cutlery industry clustered in Sheffield in Britain, or the jewelry industry clustered in Birmingham. American examples from more contemporary economic life would include, of course, kind of Silicon Valley, also Detroit, Las Vegas, and maybe a less well-known example that has, you know, been an inspiration for a lot of case studies, which is the kind of carpet industry in a relatively small town in Georgia. So just to put some pictures on those ideas, here are some pictures from Holmes and Stevens's handbook chapter that I find you know, inspirational. Here you can see the clustering of large manufacturing plants in the United States, both in 1947 and in 1999, where, you know, those of you know the US population, you can see immediately that this is more clustered than is population as a whole. Some famous examples include the so-called manufacturing belt around the Great Lakes and Northeast region, and the Piedmont region in the Southeast. Zooming in a little bit more, we can look at that by industry. Here's not a manufacturing industry, here's an agricultural industry. These are 6 crops for which satellite data and other sources can reveal output, you know, a proxy for output, or at least land use. At very high granular level. And you can see immense clustering of this type of activity too. Another industry that is shown in red here, that's just another crop, you know, sugar beets. And then there's the sugar beet processing industry, or sort of, you know, the downstream industry from the crop. That's, I suppose, a manufacturing activity, but it is similarly clustered. You know, no surprise, you know, the sugar beet refineries, the plants, the production plants, we should say, not the green plant in the ground, but the production plant tends to locate next to where the sugar beets are. And so that's a sense of kind of co-agglomeration of 2 industries for, you know, probably very obvious reasons. Finally, a nice example to think about is just one particular firm's plants. These are the plants of Anheuser-Busch, which is, I think the leading brewing company in the United States. Here are their breweries circa 2000, according to publicly available information. And as you can see, they have a sort of sense of clustering, but perhaps that's because there's only 10 of them or something, and those 10 have to go somewhere. They're indivisible objects in some sense. And they tend to be near where the people are. No surprise, beer is the type of thing that is expensive to ship once it's been brewed and bottled. And so a transportation cost minimizing place to put it would be some sense close to where the demand is. So in terms of digging more into the numbers there, not just the pictures, a great reference point for that kind of activity comes from the work of Ellison and Glaser in the JPE in 1997. I'm not going to go into all the details of this paper. I wanted to just flag some of the main highlights. It's an important idea, I think, for economists in general to keep in mind that, when we were looking at those pictures, as we already saw with the Anheuser-Busch breweries, there were only 10 of them. Of course, the fact that there were 10 is an endogenous choice by that brewing company, but let's put that to a side. Let's suppose there were going to be 10. There's sort of a sense that, those 10 will look clustered because there are only 10 of them. And so Ellison Glaser developed what they call a so-called dartboard approach that tries to ask, well, how much clustering would we expect to see just by chance if economic activity was in some sense indivisible? Again, think of maybe a brewery as an example. It has to go somewhere. It is indivisible, and if there's a relatively small number of them relative to the spatial units that we can study, then there would be a natural tendency just by chance for economic activity to look clustered, within a given industry. So they develop a particular kind of statistical model that, it's in some sense special. To really adjust for this, we would have to sort of know the true data generating process of the world, which is sort of part of the goal of this whole research to begin with. But not a bad starting point from Ellison Glaser is to think about this dartboard approach. And as a side point, if you're interested in kind of sense of confidence intervals on the numbers Ellison Glaser are about to talk about, then Duranton and Overman is a good reference for that as well. So here are the results that come out of the Ellison Glaser idea. And again, I'm sorry I can't go into all the details for lack of time, but let me just say that gamma, which is shown here in this histogram, the histogram is a plot of all the I think 3-digit industries in the US production. Gamma equals 0 would be their benchmark for kind of no excess clustering. That would be if there was no tendency for the location of an industry in space to be anywhere near another unit of that industry in space. That is, if we thought within an industry like the automobile industry, the data generating process would generate uniformly distributed auto industry plants, then the auto industry gamma would be 0 in the Ellison Glaser index. And as you can see, for most industries, it's not 0. It's often above 0 and often considerably so. So that's sort of the main takeaway here is that correcting for the dartboard phenomenon, there is more clustering than you would expect to see by chance, according to the Ellison Glaser model. Just to kind of dig a bit more into that, here are some examples, some industries that you might expect to be fairly highly spatially clustered, such as I've already mentioned, the automobile industry, the auto parts industry, the carpets industries. These are all industries with pretty high, as you saw in that spread of kind of between 0, no clustering, and it's the maximum in their data. Some other industries that are intriguing for their lack of clustering, would include like the concrete industry. We tend to think that is extremely difficult to ship, and so there'll be no surprise that has a low gamma. It needs to be near where the demand is, and if the demand is relatively spread out, like where the people are, then the concrete industry would not be very clustered. Ice is possibly another example. Newspapers, this is probably from a time when lots of local newspapers still existed in the US, and so that was, inherently not that tradable an industry. And of course, we can get back to the kind of the beer industry example as well. Here are all the top 15 and bottom 15 industries in the Ellison-Glaser numbers. One to keep an eye on at the very top is wine. Again, why is wine so clustered? Well, I don't know, but of course, a natural explanation could be found in this type of picture. We do see that the agricultural activities, crop-specific economic activities, such as the grapes that are used to grow wine, mostly, of course, on the West Coast, more or less, in the case of the US. Those things are very clustered too. The rice industry is clustered, the flaxseed industry is clustered, the durum wheat industry is relatively clustered with 2 clusters. So, when you think of these clustered industries, it's important not to just think of Silicon Valley and other, manufacturing-like industries such as automobiles. We have to remember that the fur goods industry and the wine industry and the oil industry are clustered too. And that reminds us, that there can be a whole range of reasons for this sort of phenomenon. Okay, so towards that goal, Ellison-Glaser 99 extended their 97 paper in a small but interesting way, and they basically allowed sort of the costs in their model that determined, the industries are in their model are selecting where they want to go on the back of a tendency to want to cluster, but also on the back of some exogenous, reasons. Let's call those kind of costs. And these are some examples of costs. So in this statistical model, they're interacting a sort of state characteristic with an industry characteristic. And so the first example shown here, the state characteristic is the price of electricity in that state, and the industry characteristic is how intensively that industry uses electricity. So there's a positive coefficient here in their regression that suggests that there tends to be a tendency for industries that are electricity intensive to locate in states that have cheap electricity. You can see similar examples with other types of resource-based inputs such as natural gas, coal, farmland, livestock, etc. Always entering positively here. So that speaks to the type of phenomenon that maybe we saw in the case of wine. That to produce wine, you need to wine is a grape intensive industry, and so you need a location that has cheap grapes, to have low costs in the wine industry. So these are obviously kind of mere associations, and they're a crude stab, I think it's fair to say, at all of the heterogeneous sources of cost variation across locations and industries. But what I find interesting about this is the effect that controlling, in a sense, for those costs, which are those cost differences, which are estimated by this regression in table 1, the effect that controlling for those cost differences has on the Ellison-Glaser index, and that's what the 99 paper does. So model A in this table is the same as the 97 paper. So the mean gamma is 0.05. We saw that in the histogram, and this is just another way of reporting the spread there that you saw in the histogram before. Model B is the same model, but augmented for the kind of cost interactions, as it says down here, that were estimated here in table 1. So for the tendency for cost differences coming from natural resource-based and other kind of possibly kind of locational fixed characteristics, if we were to control for those as best we can, how much does the gamma fall? And I find it intriguing that it doesn't fall very much. It falls from 0.051 at the mean to 0.048 at the mean. You can get it to fall more by including other things. Those are industry fixed effects, C and D of various sorts. You know, that I think stretches it a little bit because you know, it's stretching the point beyond what I want to sort of focus on for now. But you know, what I find interesting for now is that controlling for these types of natural kind of cost characteristics, at least as best as, you know, as one can in this kind of attempt, not obviously perfect, but I would have, you know, thought this is a pretty good first step. Controlling for those things doesn't do very much to the extent of clustering we see. So it appears to be that people are, that these industries are clustering for reasons that are not to do with the characteristics that are shown in this table 1 regression, as you know, characteristics as kind of weighted by the coefficients in the table 1 regression. So, you know, that tells us that there's a lot of scope for clustering along, you know, because of other reasons. And that is a good summary of where, you know, at a very high, rough level, why economists would say that this type of output, industrial output and output as a whole, can be so aggregated spatially, agglomerated spatially. Okay, so the first one is the type of you know, natural advantage or natural resource-based cost differences that I was alluding to earlier. So you know, a great example, as I've already said, is the wine industry, right? We know that the ability to produce grapes is, you know, for whatever reason, extremely spatially clustered. There's very few places that have the right climate and soil and everything else needed to grow wine and grow grapes in the United States, the right type of grapes. So that type of natural input into wine production is already agglomerated, you know, for whatever geological or natural reasons. And so it's perhaps no surprise to see that that industry is also agglomerated. You know, it's just locating near to its inputs, and its inputs, natural inputs, are already agglomerated. But you know, the other main category of source of, you know, reason why we see agglomeration is going to be a form of endogenous agglomeration, endogenous source of agglomeration. So, you know, one easy, you know, point number 2, easy to kind of get off just to state is that you know, it could be that people, factors of production, that is, you know, workers and human capital, and the things they bring with them, like their machines, you know, are agglomerated for reasons that have nothing to do with production. So, you know, economists call that a consumption amenity. You've already seen that in some of the earlier lectures. You could think about this as just, you know, that for whatever natural reason, you know, nice places to live, like ocean views or nice climates, or you know, cheap inhabitable land is in some sense already agglomerated. You know, that's possible. You know, we can certainly think of examples like that. Okay, so both of those are kind of, in a sense, exogenous. You know, they're to do with something to do with the geography of the terrain that kind of humans are given to live on. Point number 3, though, is about endogenous sources of agglomeration. And so here, you know, we appeal to a notion that of a sense in which either production is more, you know, output, that is the act of producing, is more productive because of the presence of others who are doing the producing. And that sort of positive externality, you know, sometimes called a spillover, is kind of the classic source of answer to the question, why is economic activity so agglomerated? The answer often given is that there are, you know, agglomeration. You know, it bears mentioning, though, of course, that we could also have positive externalities in amenities. that is in the production or the the act of generating the amenity, I suppose is the right word. Here, I guess you just have to think about examples, where it, for whatever reason, we don't need to go into the details. It's very likely that humans just enjoy being near other humans, right? So that would be a positive externality in the kind of in the act of living in an area. You want to live there more if there are other people living there. Now, obviously, we can think about negative externalities too. Some of the earlier lectures have talked about those as well. But here, in terms of explaining why we see agglomeration, we would potentially appeal to positive externalities. Okay, so that's a very rough overview of sort of the two types of answers to the question of why output is so agglomerated. And these are often kind of simplified, particularly by geographers, into so-called first nature sources of geographic agglomeration. Those are the exogenous locational characteristics that affect productivity and amenities. And for whatever reason, beyond our purview, those exogenous locational characteristics are already agglomerated. They're not perfectly uniformly distributed over space, right? We have coastlines and natural harbors and valleys and good climate and good views and good soil. Those things are not uniformly distributed, and so those first nature geographies could already potentially explain the clustering we see. And to the extent that those first nature geographies can't, then we could appeal to second nature geographies, endogenous locational characteristics, where the very act of people being there changes the payoffs to other people being there, whether those payoffs are in production or amenities. And those are endogenous, because if the first people weren't there to generate those spillovers, then the second people wouldn't want to come. So we're now going to after that very high level introduction to those two sources, we're going to dig into this a little bit more. So the first model that might be taught properly in a course in this area on economic geography, might be the very famous, very influential so-called core periphery model that Paul Krugman published in the JPE in 1991. So I'm sorry, I don't have the time to do justice to this. There are many textbook treatments that could do far better justice than I could anyway. But let me just sketch the main idea, because it is an important thing to at least know about. So the basic setup of this, very toy-like model, it was boiled down to its kind of core essential ingredients, so that Paul Krugman could make the point as parsimoniously as he could. Has just two locations, and they're actually completely symmetric. So already there's no kind of first nature geographic differences at all, right? So the geography, the exogenous geography, is uniform in this two location world. Okay, so then we're going to have, in terms of production, two sectors, two activities. This two-sector model, actually, kind of recent work that I'll be talking about in a little bit, has actually backed away from. I'm not sure if there are necessarily good reasons for that, but the two industry model is key to the Krugman model, and so it's important to keep an eye on both of these two industries. Okay, so the first I'm calling A for, let's say, agriculture. This is a constant returns to scale industry that's completely plain vanilla economics. It's homogeneous good with perfect competition. The second industry is labeled M for manufacturing. This is really just a canonical Dixit-Stiglitz industry. So that is to say, it's monopolistic competition with free entry, CS demand curves with an elasticity of substitution sigma, that all of those homogeneous firms in the Dixit-Stiglitz model are facing. They have their own variety that they produce, and it has an elasticity of demand, of residual demand, sigma. In terms of setup to to more recent work and work that I'm going to talk about later today, is to say that within this M industry, everything that is done in a Dixit-Stiglitz model like that turns out to be kind of, at the aggregate level, so that is the only level that's going to matter for any of the points we talk about today. Everything is isomorphic to a much simpler, I think, model in which there is just a completely normal, perfectly competitive, constant returns to scale production, but there are external economies of scale in that industry. So that might sound a little weird. I don't have time to go into it. You can find a lot of discussion on this point elsewhere, but it's an isomorphism that I find helpful and find worth remembering, because I can always map from the more complicated Dixit-Stiglitz model that has all this complicated process of kind of firms and markups and entry going on, and just remember that at the aggregate level, that is at the sector level, within sector M, everything is as if there's just some external economy of scale. How strong is that external economy of scale? Well, it's got a constant elasticity, first of all, in that economy of scale function, external economy of scale function, and the elasticity is governed by sigma. The lower the sigma, the stronger the economy of scale, the as if external economy of scale. Okay, so two sectors, A and M, and that's a key feature. Another key feature is transport costs. So these are the so-called iceberg form. I'll talk more about that later, but this is basically just, there's just a productive cost of transporting, nothing more fancy than that. And let's let this thing phi indicate sort of the inverse of tau. So it's kind of tau to the 1 minus sigma. Sigma is going to be bigger than 1. So this is kind of an inverse, sometimes called the so-called freeness of the trade. Finally, we have to talk about the factors of production that enter this constant returns to scale production function and the one inside the Dixit-Stiglitz firms. This is going to be very simple, a single factor of production, call them workers if you like. However, there are two types of workers. They don't enter differently into production, but they are different in one sense. All workers are free to move across industries, but a fixed fraction of workers is stuck in their location. Another fraction can move, and the fact that they can move turns out to be very important to the logic. They're going to sort of seek the location. They're free to move, so they're going to maximize utility when they move. And maximizing utility here means basically just finding the location with the highest real wage. Okay, so what's going to happen in this model is that it's fairly simple to state in words. These as if external economies of scale in the manufacturing sector, in a location, mean that if we did happen to have a lot of these freely mobile workers go into a given location and go into the manufacturing sector in that location, then thanks to those as if external economies of scale, that sector would get more productive. That would mean, in a sense, that they can generate a higher real wage. Remember, the firms get more productive, but there's free entry, so they don't make any more rents when they get more productive. They pass it, as it were, through entry fully on to consumers. And so, there's already this sense in which, if a lot of people live in a place, then thanks to external economies of scale, it's going to be a productive place in terms of producing utility. And so now even more of these mobile workers are going to want to live there. That's the basic mechanism going on in the model. However, we do need these transport costs to exist because if they, obviously if trade were free, then there would be no reason for somebody to want to live near a productive location. They for consumption, for the real wage that they would earn there. At least for the cheap goods, they could earn those. They could consume those cheap goods from anywhere. You do need the some transport cost, basically. Okay, so that's the main intuition of the model. Here's the main result of the model. As Brakeman et al. Have illustrated it. What we can plot here is kind of all equilibria, basically, in this model as a function of the one parameter which we're going to change, which will be that freeness of trade parameter phi. So remember, freeness of trade 0 means autarky. These places don't trade at all. Freeness of trade 1 means fully free trade, right? So by moving along the x-axis, we can explore a fall in trade costs. The thing that's plotted on the y-axis, so-called lambda 1, is the share of the mobile workers who choose to go to location number one of the locations. So this is a notion of how clustered is economic activity in this model. So lambda 1 equals to 1 means that everybody, all the mobile workers, live in location number 1. Lambda 1 equals 0, of course, means none of them live in that location. And lambda 1 equals 0.5 means that we have a non-clustered distribution. We have half the mobile workers living in location 1, half of them living in location 2. So that's a sort of symmetric or dispersed outcome for lambda if we had lambda equals a half. Okay, so what also is shown in this model is kind of an ad hoc sense of dynamics. The model is static, but we can think about an ad hoc process by which sort of that indicates in which direction would a mobile worker want to move, if they were the only person moving, kind of an ad hoc but individualistic sense of stability, or a sense of dynamics. And those dynamics push in the following direction, that if we were ever in this parameter region, that is with kind of quite high trade costs, anytime a worker is, if the lambda, remember the dispersion, were kind of very low, below a half, that is if most of the mobile workers were in location 2, then some of those mobile workers would want to move. They wouldn't be earning a high enough real wage in that location to justify living there. They'd want to move to the other place. And that force kind of pushes up if we were starting below, or pushes down if we were starting above. And the bottom line is that at very high trade costs, that is, remember, this region of the freeness, the only equilibria here are going to be, the only stable equilibria, I should say, are going to be symmetric equilibria. So and that's what the solid line here shows, is all stable equilibria in this model. So if we were to sort of start at a stable equilibrium, like here, for example, and then reduce trade costs, increase the freeness of trade, we could keep doing so, and those points would remain, the symmetric dispersion of people, half the people in each location would remain the only stable equilibrium. Until we reach a kind of critical value of concentration, or dispersion is no longer stable. It can no longer be maintained. If phi were to go any higher than that, if trade costs were to go any lower than that point, then the marginal worker who's considering moving would decide to move. And if that person was considering moving kind of to location 1, then she would want to do so, and so would everybody else. All hell would break loose, and this previously stable equilibrium here would no longer be stable. And the only stable equilibrium from any point that starts in the blue area would be the equilibrium where everybody lives in location. All the mobile people live in location 1. Likewise, if we were to start in the red region, if the deviation is considered in the down direction, then the only stable equilibrium that would hold would be down here. So we see this kind of endogenous clustering happen in this model as the trade costs fall below a critical level. That is to say, there used to be not clustering, there used to be self-reinforcing advantage from external economies of scale takes over, and you get clustering. That is, you get the mobile workers either living in location 1 or all living in location 2. And those remain the only stable equilibria as you continue to reduce trade costs. So this model, it's very simple, but it's very rich. It illustrates a key phenomenon for a key possibility, economic logic in which we can get the phenomena we were talking about earlier of the clustering, but also how we can not have it. We can have, if trade costs happen to be in a range, we can also be in a range where clustering is not what will happen economically, or it can be what will happen economically. In this model, it all depends on this phi thing. And remember, I should have stressed this, sorry, phi is, of course, remember, not just trade costs. It's trade costs to this power that involves the sigma. And so it inherently involves a notion of also the strength of the economic, of the as if external economies of scale. Okay, so now the final thing, of course, to remember about this is that all this static model really says is a notion of equilibria. And so the equilibria here, the ones that at least are stable, are shown here in solid black. And so in this region of phi over here, we of course have multiple equilibria. We have the fact that either agglomeration in location 1 is an equilibrium, or agglomeration in location 2 is an equilibrium. They're both equilibria, and the model says nothing about which one would happen if you were just staring at your model in terms of fundamentals. And of course, that's just the classic economics notion of multiple equilibria. Okay, so the basic features of that kind of model have, which have appeared in many other models as well. If you're interested in textbooks, again, see my last slide. But the basic principles of those kinds of models are kind of the existence of agglomeration externalities. That is kind of the source of those second nature geographies. We've already seen Ellis and Glaser. They think those things exist. They think there's more clustering than you could get from just natural advantage, especially in many industries, most industries. Case studies like in-depth anthropological studies of what happens inside a place like Silicon Valley speak to this too. Some recent work, which I know you've seen, Steve Redding, he talked about the Berlin Wallpaper. That's within a city. The similar ideas have been used to study agglomeration externalities across cities. I shouldn't say across cities, but sort of 4 spatial units that are an entire city, not a neighborhood within a city. For evidence of that kind of thing, you could see, for example, Greenstone, Hornbeck, Moretti, or Klein and Moretti's work. The existence of those kinds of externalities is, there is evidence for those sorts of technological parameters, you might say. And so the implications of those things we've just seen. We've seen in the Krugman 91 example, the potential for multiple equilibria. I'm going to get into some of the details of what I mean by these phrases later today, but just to fix ideas in order to motivate some motivating evidence I'm about to talk about, we could ask in a sort of, if we were to imagine a dynamic version, a truly dynamic version of something like the Krugman model, we could try to ask, not are there multiple equilibria? There might be, but we could ask a sort of more modest question, which is, are there multiple steady states, stable steady states? So again, in this static model, I can't talk about that per se, but in a more dynamic model, I could. And if there are multiple steady states, then there would be the potential for what, in the dynamical systems literature gets called path dependence. That is to say, for initial conditions, or kind of, who knows what initial is. So you could always define initial as the beginning of time, or you could define it as just kind of some point in the past. So it's either long redundant shocks that affect your notion of what is initial, or even just genuinely the beginning of time initial. Either way, events in the past can matter. in the picture. If this were a genuinely dynamic system, then we could use the language I was using earlier and sort of say that if for whatever reason we were currently at one point in time at an equilibrium, say here in the red region, this red region is the so-called basin of attraction of the equilibrium of the steady state in which everybody agglomerates in region 2. And so in other words, the dynamic system would be saying, if you start in the red region, you're in the basin of the steady state. That means that the only stable state will be down here. That is when everybody mobile lives in location 2. So in other words, history matters because if you were to start in the red, you're going to end up with everyone living in location 2. You're going to start in the blue, you'd instead end up with everyone living in the location 1. And over here, we say, well, history cannot matter ever because no matter where you start in yellow, you end up with everybody dispersed. So in the yellow region, kind of history does not matter. There's not path dependence, but in this blue-red region, there is. Okay, so obviously the existence of such path dependence is, some people would say it's of interest in its own right, but obviously its main interest is from a policy perspective. One way to think about this is in a positive sense. That is to say, that if we do live in a world with such path dependence, then it could be the case that kind of cheap policies, cheap, I'm not sure what that means, but think about it as kind of policies that are very cheap relative to their benefits, could, in a sense, kind of nudge an economy out of the basin of attraction of a bad steady state and into the basin of attraction of a good steady state, and that would be a great kind of policy to pursue. It would really fix a market failure big time. The flip side of that, of course, is that if we live in a world of path dependence, then policymakers need to beware. It's like if you're trying to do your best, let's say you're deciding where to put highways in the United States, 60 years ago, and you're doing your best, you need to acknowledge the fact that wherever you put them in a model with path dependence is going to generate economic activity around where you put them. So, you need to sort of not only get things right in the short run, but also in the long run. And so in a world of path dependence, it's an incumbent on policymakers to be extra careful, I suppose one could say. Okay, so before we get back to theory of so-called path dependence, I'm just going to say a few words about direct empirical evidence for such things. A very well-known, very well-executed study of these, exactly that, comes from the work of Davis and Weinstein in the AER in 2002. This is a pioneering study that said, well, it's but a very intuitive idea. It sort of said, well, if these path-dependent phenomena are truly real, then we would expect that, if you took an economy that was already in the basin of attraction, or maybe even in a particular steady state, and you were to sort of perturb it by a certain amount, let's say enough to knock it out of that basin of attraction and into some other one, then you would expect that perturbation to have permanent effects. That's basically a corollary of a world of, if we live in a path-dependent world spatially, we would expect it to be at least possible for perturbations, large perturbations, you might say, to knock you out of the basin of attraction of one steady state and into another one. And that's the basic logic of what Davis and Weinstein were trying to do when they looked at the implication, the consequences of World War II bombing in Japan after the war. These findings have been looked at in other settings too. This is just a short list. And Davis and Weinstein also, in later work, 2008, looked at the fate of not just locations, but industry locations, which I think is sort of extra interesting. So here's their main finding, in case you haven't seen this before. So two obviously heavily, tragically damaged cities with not just damage to the infrastructure of the city, as it were, many buildings, most buildings, but also damage to people, to human capital through death and outmigration. These two cities, Hiroshima and Nagasaki, bounce back, one could say, in terms of just the crude population count shown here. They reverted to model kind of fashion. That is to say, you had faster growth when you were knocked away from a previous steady state. If we could imagine that sort of 1940 was something like a steady state. And so that's kind of exactly opposite to what you would expect in a spatial path dependence model. This is what you would expect in the standard faster return, not only return to the steady state, but faster growth after the shock, and then a smooth asymptote to the return. Digging beyond just those two cities, these authors plot the growth rate kind of during the war, which of course is highly negative in terms of population for many cities, including the two ones that had the biggest destruction that are shown here, Hiroshima and Nagasaki. So those are negative growth rates during the war, and that's plotted against the growth rate after the war. And there is, again, exactly what you'd expect in, remember, those kind of Barrow regressions, Barrow-Selle-Martin kind of convergence, reversion to the mean kind of prediction, that anybody who had a big negative shock during the war will have above average growth after the war, and vice versa. So that generates a downward sloping prediction, and that's roughly what the data seems to be saying happened in Japan. They look, as I said, again at this industry by industry, and you can see something similar for employment by industry. So this is by industry by location. So now there's many more dots here. There's a dot not just for every city, but for every city and manufacturing industry. Yet there is similarly this tendency for a downward sloping relation between war, decade growth rates and post-war decades growth rates, and that these are the pictures within industries where each dot now again is a location, and you see maybe you have to squint a little bit more in some of these cases, but for example, textiles and apparel illustrates this very well, this downward sloping relation. So a lot of economists would look at these findings and say this is exactly not path dependence at work. These are these dramatic, devastating shocks to both human and physical capital led to a rebound kind of in exactly the places and the industries that were hit most, which is very consistent with a single equilibrium, single steady state kind of model. Now, obviously, this is a special setting. This is a wartime setting where other things could have been going on that maybe acted to kind of recreate the country the way it was. You might imagine there's a tendency for that after wartime destruction, but the findings as they are, should already get us thinking about the potential for, in a setting like this, a single steady state. I think. So another very nice study on this theme, the last one I'll talk about before the break, before the questions, which will then set up our break, is the work of Bleakley and Lin in the QJE in 2012. So this is another very nice study that looked at a setting where there was an event in the past that, in a sense, removed that location or location industry, you could say, that removed the location's natural or a source of advantage that it had. So in the case of Hiroshima, the language I would therefore use in the case of Hiroshima is that you could say that for whatever reason Hiroshima had some natural or endogenous advantages circa 1940. The atomic bomb destruction removed those, yet even after they were removed, the city came back. Right? So that's sort of the lack of path dependence. Bleakley and Lin are going to do something analogous, but very different. They're going to look at what people call portage sites. So this is, if you want a great example of this, think of the word Oxford or Frankfurt, which of course just comes from a sense of the place on the River Thames, an example of Oxford, where it was, for whatever reason, relatively easy to ford the river with one's oxen. That's how the name came to be, I'm told. So that was, in some sense, a good place, a place where people they cross that kind of river. So Bleakley and Lynn look at something a little different, which is called a so-called portage site, which is really just a place of transshipment of goods from one type of boat to another type of boat. And this is an era, sort of think roughly 1800 in the United States, when there were no canals, there were no railroads, basically. And so these sites where people had to move, if you wanted your goods to traverse a river, you would have them in one boat, and then you would, at the portage site, have to sort of take the goods out of the first boat, put them on shore, and then lift them over, you know, whatever obstacle was in the way, and then put those goods in the upstream boat, and the upstream boat could then take the goods further. The points where that had to happen were so-called portage sites. Okay, so in terms of to try to predict where portage takes place, it takes place at lots of places, but to predict where it would take place, Bleakley and Lynn appeal to a very nice idea, which is that there is obviously there is, when a river leaves, kind of, if you were traveling upstream from an ocean, upstream along any river, there is, of course, going to be a point where you can no longer travel in your boat because of the emergence of some rapids or kind of small waterfalls. That's the point where your boat can no longer traverse the river, and you would have to, either lift your boat out or lift the goods out and put them in another boat. So in the US, it's easy to predict where the first rapids will be because of a geological feature called the so-called fall line. It comes from the notion of waterfalls. And so this picture, might be a little bit hard to see depending on your resolution, but illustrates a picture of the Southeast United States, and the fall line is shown here in black. That's the geological feature of kind of where the fall line is. It's something to do with different layers of rock and sediment. So what's maybe a little harder to see is the rivers that are shown here in dotted lines. So let me zoom in on the area around South Carolina. So this is a major, let me get this right, sorry. Yeah, this is a major river that goes upstream to the town of Columbia, which I believe is, I believe is here. What's shown here in the blurry background is density of population, or lights, in the United States today. So maybe let's look at this picture of Columbia. So there's a river that's leaving the Atlantic Ocean here and going, if you were traveling upstream, eventually you would cross the fall line. And it turns out the point where you cross the fall line is the town of Columbia. That's the first place where that river becomes non-navigable. So, and those of you who know South Carolina would know that Columbia is, to this day, the largest city. It's the state capital. It's the site of the state university, et cetera, et cetera. And Bleakley and Lynn talk about the tendency for that to be true. That is for agglomeration of people, cities today, in locations that are at the intersection of the fall line in black and all kind of navigable rivers as they leave the Atlantic Ocean. And there are some extreme examples here, like I believe Dallas, if I'm not getting this, I'm probably getting this wrong, but I believe Dallas is here, and even that is a fall line city. But there are lots of other examples, as you can see, just tracing this line too. Some of them are named here. Here are some others that are named in the area of Washington, D.C., Richmond, Virginia, et cetera, as well. Okay, so that's just visual evidence. What about the analytics, the statistics? Well, this figure says it all. It says that if you pool non-parametrically across all rivers and sort of stack all the rivers one by one and just look at the tendency of lights to locate along the river, there is a tendency for those lights to agglomerate at the place where the distance along the river from the fall line is 0. That is where the river crosses the fall line. That's what this big peak here is saying. There's even a nice indicative possible tendency here of people to not want to live just downstream of the fall line location, right? And that's sometimes the fall line location, they probably don't also live just downstream. Okay, so what does this have to do with path dependence? Well, the thing about the fall line and the portage activity is that once canals and railroads were built, let's say by 1890 or so, all of these portage sites had, my understanding, had either a canal or a railroad or both. Allowing those boats to be lifted without the need for huge amounts of human beings to do the portage. The boat could just use the canal and travel upstream around the waterfall, no problem. But there's still this tendency for cities today to be located in these portage sites, and Bleakley and Lynn document actually that tendency is, like, if anything, still growing. It's not as if it's dying slowly. It's actually possibly still growing. So this is actually a positive example of path dependence. This says that you remove that source of natural advantage, that is a portage site. By the way, of course, portage in itself was a bad thing, but the fact that it required so much human labor to help do the portage became a good thing for labor demand. So that's why I'm referring to it as a source of natural positive advantage. But so even nowadays, 200 or maybe 100 years after the natural advantage of the portage sites was fully killed off, we still see a strong tendency for location of economic activity today at those sites of former natural advantage. And that's exactly consistent with the logic of path dependence. So, to sum up, the evidence for this is highly mixed, I would say. These are just two examples of empirical papers I've mentioned. Two very nice examples. One where major destruction did not leave evidence of path dependence in post-war Japan, and one where kind of the slow destruction, you might say, the slow death of the portage industry throughout the 20th century or the 19th century did not lead to the death of the cities that were located on top of those sources of natural advantage. And so I have here some more findings from the Bleakley and Lynn paper that I'm gonna kind of skip over, but obviously you should take a look. And now I'm gonna pause for some questions before we take our break.
Terrific, thank you very much indeed, Dave. So we've got lots of questions in the box here. We've got 2 or 3 questions with lots of upvotes here asking about the Ellison and Glaser model. So I will ask them, and then a couple of broader questions. So first question, which has received a lot of upvotes here, is asking about, in the Ellison and Glaser paper, it's difficult to interpret what exactly the gamma means. So could you provide some intuition as to how to understand what an excess gamma of 0.1 or 0.5 or any other level means?
Sorry, I cannot. Sorry, Brad and the upvoters, but I cannot. I would have to go back and read the paper more carefully. I mean, I find it. I mean, I'm sure the paper has a good answer. It's just I can't recreate it. There is something obviously indicative about comparing ice to wine, or the other examples I had there, newspapers in an era of local newspapers, and then before the internet, to wine. That should already paint some pictures in your head. But for other pictures, yeah, I guess you'd have to look at the paper and come to think of it. Another picture that's in my head is some pictures in Duranton and Overman, where they had kind of real plant level location data for very nice spatial resolution. And for the case of the UK, and so you could see some examples of different gamma industries. So I don't have those with me, but the Duranton Overman 2005 Review of Economic Studies paper would have those, as I'm sure it does much subsequent literature.
Terrific, thank you. So let me perhaps ask the next 2 questions on the same paper together, and then we can get to the broader ones. So the second question here talks about the Dartboard approach aims to discount the extent of agglomeration that may be due just to the fact that there are some firms that produce an output, but some of the same forces that might lead to spatial agglomeration may also lead firms to want to concentrate the activity in a firm. So does the Dartboard approach go too far in discounting these forces? And then a separate question on the related to the Ellison and Glaser paper. So when you say natural inputs are agglomerated, do we have comparable gamma measurements for natural resources or other types of input?
Yeah, thanks. Two interesting questions. So yeah, the first one, I mean, you're right that they took the plant as the fundamental indivisible unit of analysis. My recollection is they let there be a different divisibility factor, we might call it, in each industry, and they calibrated that to match kind of US data on the number of plants per industry. But of course, as we saw from the Holmes and Stevens example of Anheuser-Busch's, what is it, only 10 brewery locations for the entire United States of everything Anheuser-Busch brews, we know that that in itself already reflects some economies of scale inside the firm in the case of that Anheuser-Busch example, and that is, presumably endogenous. I mean, if Anheuser-Busch was living in a bigger United States, would they choose 20 industry plants, or if the United States was twice as big in terms of population and size, would they have chosen 20 plants, or would they have chosen, I don't know, the square root of 14 plants, or would they have chosen something different? I don't know, but Don raises a very good point about that, that we're conditioning on that type of agglomeration already, which is itself, as people know, can differ across space. So the optimal size of the plant when located in like a suburb of St. Louis is probably very different than when it's located in a brewery in Brooklyn or something. And so the very act of spatial location changes the optimal plant size, even independent of local density factors. So that's a very good point. And then the second question about natural inputs. So yeah, I'm not aware of an attempt to go down a list of natural resources or things and construct gammas for those. What I was trying to evoke was that the Ellison-Glaser 99 results that I did talk about very briefly are kind of doing something like that. They're sort of trying to say, well, in their model, there's a potential cost difference across location and industries. Some of those cost differences might be just exogenous, to do with natural resources, let's say. Let's try to estimate the effects of those costs, that is, for example, the presence of cheap electricity on propensity for firms to want to be there in a given industry, and then let's subtract that off. So, I guess you could think that sort of deep down inside their estimates, they did have a gamma, set of gammas for all those different industries, and then the results I was showing were just weighting those different resource gammas separately by how important those resources are, separately by industry, in order to come at after an overall correction factor to then subtract off in the way I tried to explain it.
Excellent, thanks. So next question here, so relates to clustering and immigration. So could clustering be a result of groups of immigrants that happen to settle in a given area? So for instance, if immigrants are more likely to pursue types of activity that are common in their home country?
Right. Yeah, I mean, I see the way that Brad has already answered this, and thanks, Brad. Please keep doing that, because I would agree with what you wrote. I mean, I would see that as obviously not just people want to be near other people, form of endogenous amenity, as I called it earlier, but Canadians like me wanting to be near other Canadians, perhaps, and immigrants in the United States might co-locate in that way. For a sort of, that would be the amenity reason. Yeah, I mean, people have talked about the productivity reason as well. That sometimes an example that comes to mind is that the act of searching for a job that's a good match, maybe involves a social network to kind of grease the wheels, as well as, of course, possibly rent seek. But and that would be, if you view the greasing the wheels version of that, that would be a productive benefit of people with rich social networks co-locating near each other. They would actually get to the right match jobs faster.
Great, thanks. If we can squeeze in one or two more here. We've got a question here. So you referred in one of your earlier slides to, so this is quote, cheap policies to promote movement to a better steady state. So the question's asking about the extent to which, so perhaps cheap ex-ante policies to guide towards a better steady state is easier to think about than, for instance, cheap ex post policies for undoing ossified path dependence?
I mean, in the types of models I'm talking about here, I was imagining a policy as nothing more than, in a sense, a subsidy for some people to move. So in the Krugman model, you know, imagine we were in the basin of, imagine this was truly a dynamic model. It's not, but imagine it were, and we were kind of currently here. And sorry, let's furthermore imagine that this is not a symmetric location model, but it's asymmetric. So one location is actually better at producing than the other. So you know, subsequent work to Krugman has shown that with some amount of asymmetry, something like this picture can still hold. It'll change the details a little bit, but the basic qualitative features don't go away with, you know, with some exogenous asymmetry in terms of good locations and bad locations. So in that sense, you could imagine that, you know, imagine we were here, but the location 1 is the good location, right? So society would be better off if everyone, not everyone, but if these mobile workers were agglomerating in location 1 instead of location 2. And yet we're at this point currently in the basin of attraction, the red basin, the basin of attraction of location 2. And so a subsidy that's small enough to tip some people, some of those mobile workers to here, would then be enough to then the dynamics would take over and take the economy to the good steady state up here. So that's all I meant by cheap, was just something to do with the mass of people you need to move. So clearly that policy would get more expensive the further we are from the boundary of the basin of attraction. So, you know, if we were already starting in this steady state, it would of course be very expensive. You'd have to subsidize a lot of people. But that's the basic logic I was trying to talk about there. And so, Brad, to answer your question about the ossified bad steady state, yeah, in this model there is no such thing. I mean, the policy I was sketching was just purely a function of how many people have to be moved in order to get to the boundary. And it's true that if you're in the bad steady state, then you're far from the boundary, and so that's going to be costly. But it's kind of nothing per se to do with anything other than just the distance to the boundary.
Fantastic. Thanks very much, Dave. There was one more question about the Bleakley and Lim paper, but Jeff Lynn and Jonathan Dingle have already posted some answers. In the interest of time, I think we will stop and go to a break there.
What I'm going to do now is try to pivot a little bit, and as I warned you, into a direction that involves some of my own work I've been doing with Treb Allen. This is going to be now a discussion, a much more detailed discussion about a concrete model of the kind of phenomena we were discussing earlier. And this is going to be a setting applied to kind of US, the same sort of historical context as Bleakley-Lynn. Okay, so some of this content you'll have seen maybe in analogous forms in other lectures. So for example, a lot of these features will share in common some of the material you saw with Steve Redding's lecture on Berlin, on intra-city models, for example, the Alfeld et al. Paper on Berlin. But here it's not about locations within a city, it's about locations within a country, right? Sort of cross-city issues, you might say. Okay, so cities are things I'll call I. And this is going to be an Armington model of differentiation, just in case you haven't seen that before. That's short form for saying that, you know, for whatever reason, it turns out to be the case that locations produce different goods. They produce their own good, their own sort of Armington differentiation. We can microfound that, of course, in lots of ways, but for a lot of the issues I'll be talking about today, the microfoundations wouldn't matter. What would matter is that there is some differentiation. Okay, so locations will have some exogenous characteristics that are arbitrary, it can take arbitrary values. Productivity, A bar, the bar will indicate exogenous, and U bar for an innate amenity that they offer to people who live there. And then there are going to be kind of transport costs indicated by tau ij, as well as migration cost indicated by mu. So this is what we call the geography, as the set of exogenous things that are true about this setup. So in terms of talking about the model dynamics, we're going to kind of strip this down to the bare essentials. There's going to be agents who live 2 periods. You could call that kind of childhood and adulthood. And the adults are going to be the ones who kind of matter here. So an adult in period T is going to be a person who consumes, produces, and has made their decision about where they want to live. So in a sense, all the children do is they're just people who kind of get born into a location, and they're born into a location, let's say at T-1. And then at the start of period T, those former children become adults, and then they get to choose what they want to do, where they want to live, and hence what amount they'll produce and consume. Okay, so the notation we'll use is just L will be the, basically the only state variable in this model is LIT is the number of adults who are residing in location I at time T. And in our setup, there'll be thousands of these locations. And so L will be like, LIT will be a long vector. And LI0, we could call the vector of kind of exogenously given initial conditions of this model. Whatever time you're starting the model, you have to know where the people are. Otherwise, this model can't even start. Okay, so the production side of the model will bear a lot of the similar features to the Krugman model I discussed heuristically earlier. But we're going to pursue this kind of external economies of scale kind of language instead of microfounding it with the monopolistic competition with free entry and love of variety. Okay, so that is to say the total amount that can be produced in a location time T is basically just constant returns to scale and with 1 factor production, the adult workers. So it's really just A times L. But A, notice that A there doesn't have a bar on it. That A is productivity, output equals A times L. But productivity is endogenous. It's going to have these 3 components. So the first A bar I've already told you about, that's the exogenous component. And then there'll be these 2 endogenous components which capture external economies of scale. So LT to a power that I'll call alpha 1 is a kind of contemporaneous economy of scale, external economy of scale. That is to say, every firm will be more productive if there are, by a factor L to the alpha, if there are L people around today. But firms don't take this, firms are too small to have any effect on the big L, and so it's external to the firms. Okay, so that L to the alpha is very standard. That's often called kind of the agglomeration externality. It's contemporaneous. We're going to add to this something a little less standard, which is a potential other parameter, alpha 2, that governs historical spillovers. So even holding constant the number of people in a location today, it's possible that the number of people in the location last period is also a source of productivity differences in the location. If alpha 2 is positive, that means that there's a positive historical spillover. And in the paper, we discussed lots of for this, lots of isomorphisms of this with other things people have discussed in the literature. A lot of phenomena that people talk about boil down to something like this. So we're just going to start with this because it sort of represents those phenomena. Okay, so that's production. Consumption is going to be very analogous, except involving kind of welfare. So the Armington goods that each location makes are going to be differentiated varieties with an elasticity of substitution that's constant and equal to sigma across them. That's the classic Armington tradition. And so, consumers or these adult worker migrants are going to sort of decide where they want to live. And if they decide to live in location I, they're going to get welfare WI, big WI, which is really just the real wage that they'll earn in location I. That is to say the nominal wage, little w, divided by the price index, where that price index is kind of the correct CES price index for this elasticity sigma. But it also involves the amenities that you'll enjoy in location I, which we call U. And then U, again, maybe it's just a lot like A above here, has 3 components. An exogenous component, U bar, that I've already talked about, 2 endogenous components, that is to say a contemporaneous amenity spillover governed by beta 1, and a historical amenity spillover governed by beta 2. So completely symmetric on the productivity and the amenities side. And again, you can think about lots of different isomorphisms for that. And by the way, of course, these betas and alphas need not be positive. You might think that this model as written lacks kind of some essential congestion forces, like the cost of housing or the cost of land. That's another way of saying that you really want a negative beta here when all is said and done. And that's perfectly fine too. Okay, so putting that model together, we can study the flow of goods and the flow of people, and both are going to take the so-called gravity form. I don't have time to go through the derivations; those are in the paper, but they're both fairly standard. So the Armington assumption means that trade flows are going to look like this. X will be our notation for bilateral trade flows from I to J. In the natural sense, they depend on the wages at the origin, the productivity at the origin, as well as the price index at the destination and the total demand at the destination. And then also trade costs, as usual, get in the way of those two unilateral terms, I and J. The migration for people, the migration gravity equation is actually very analogous. There is a kind of pull factor, which is the welfare at location J. Remember, the big W is our notation for the welfare you'll achieve if you go and live in location J. And that's the kind of a pull factor. A lot of people will want to migrate from I to J if WJ is high. There's a, LIT minus 1 is the mass of people who are starting in location I last period. That's the number of children who were there last period are now waking up as adults and beginning their migration journey. Migration cost mu enter negatively, as you would expect. And finally, there's something that acts a lot like this price index up here for goods. This is kind of like a price index for migrants. Another way of saying it, we call it big pi. Another way of saying it is that it's sort of the expected utility of a child born in location I last period. It's almost like a multilateral index for outbound migration. Okay, so two gravity equations. This is the notion of equilibrium in this model. It's completely standard. We're gonna take as given, as I already mentioned, the vector of initial conditions and the vector of exogenous fundamentals for every location and every time period. And an equilibrium can be characterized by, a vector of L's where people live, the vector of wages, welfares, and those kind of welfare price indices pi that satisfy these four equations. And these are really nothing more than goods market clearing conditions, balanced budgets, and mass conservation of people, sort of the inbound migration equals total outbound migration kind of things. Okay, so what turns out to be easy to do when you write, when you know that all the bilateral flows are gravity-like, as they are, as I showed you earlier, and when the equilibrium is written in this way, in terms of all of these bilateral flow variables, xij and lij, is to just substitute the gravity equations into the equilibrium conditions, and then it ends up looking like this. And this is a huge system of nonlinear equations in the four types of endogenous variables. Remember the W, the pi, the L, the big W. And they are, there's one of those variables for every location and every time period. So there's kind of 4 times n times t unknowns here. But what's powerful about this system of equations, as Treb and Kostas Arkalakis have worked on a lot, is they take this kind of power form. So every time an endogenous variable enters this equation, it enters to some power. And that's going to be a very convenient mathematical property for characterizing the solutions to this system of equation kind of exactly. We don't need to linearize or anything. Okay, so the first proposition that comes out of this is about uniqueness. When will the equilibrium of this model be unique? And this is a useful result because the equilibrium, just to stress that word, is the entire dynamic path, kind of from the exogenously given starting point, whichever one you want, and given the sequence of exogenous fundamentals, this is an equilibrium is a dynamic path. And this proposition is going to tell us when the structural parameters of the model are such that you have a unique equilibrium. And that's useful, I think, very useful for empirical work, because, if the model had genuinely multiple equilibria of dynamic paths, then of course that would be like saying we have no idea what will happen. Even given some initial conditions, we don't know what will happen. But if we know that this sufficient condition for uniqueness is satisfied, then we do know what will happen. We know that the equilibrium we found on our computer is the only possible set of solutions to the system. Okay, so this is it's a little bit to take in, I know, but the intuition is that you can construct a matrix which we defined as a matrix A, whose arguments are summarized for the purposes of this discussion in terms of their dependence on only the contemporaneous elasticities of spillover alpha 1 and beta 1. There are other parameters in the matrix A, but they're always sigmas and thetas. They're the kind of sorry, what I didn't even say what theta was. My bad. I'm sorry. So, like in Steve's within urban structural modeling lecture, there's going to be sort of taste differences, idiosyncratic taste differences across locations that that everybody draws. And those are going to kind of smooth out the migrants maximization decision. If those idiosyncratic taste differences are drawn from a fresh A distribution, then you get this gravity equation. And I'm sorry, I skipped over this, but the dispersion parameter of the fresh A distribution is 1 over theta. So if and so that's what the theta is doing, is turning up here. As you saw with Steve's lecture a couple of weeks ago. Okay, so thetas and sigmas matter in this matrix, but we're not stressing that for now. We're stressing the dependence on alpha and beta. And the reason this matrix matters is because whenever its spectral radius, that is to say its largest eigenvalue, is smaller than 1, then you know you have uniqueness of this crazy nonlinear high-dimensional dynamic system. And so that's a very easy condition to check. It's just a 2x2 matrix that you just check and compute its eigenvalues to both of them and check that the largest one is smaller than 1, and then you know you have uniqueness. And an important piece of intuition to get is that alpha 1 and alpha 2 matter directly for this matrix, as I've already stressed the dependence, but alpha 2 and beta 2 do not. Those are the contemporaneous spillovers, remember, in the production function. Alpha 2 and beta 2, those are the lagged spillovers. Those ones don't matter at all for talking about uniqueness. It's only the contemporaneous ones that do for talking about uniqueness. And that comes straight out of this result. Okay, and another thing to flag here is this is true for any positive geography, that is to say, and also symmetric geography. The paper discusses the asymmetric case. But that is to say, you don't have to worry about whether you live in a very asymmetric world when you apply this result. It holds for any geography subject to the conditions I stated. Okay, so this is just a picture, for example, of a slice at values of sigma and theta that are common in the literature through that spectral radius sufficient condition. Yellow is where alpha 1 and beta 1 are low enough that you get uniqueness, and blue is where they're high enough that you can't guarantee uniqueness. So the yellow is kind of the uniqueness condition satisfied region here for a slice through sigma and theta. Okay, so in this setup, you can talk about how history matters, and this is a useful decomposition to think about. So this is always true in this model. That is to say, the number of people living in a location that is L today will naturally be higher if that is a nice place to live, if it has a high U bar or a high A bar, a productive place to be. But it also depends on some endogenous things. P, the price index. This thing, capital lambda, which is sort of another notion of migrant market access that I've defined down here. It's kind of like another price index, but for migrants. And L, the value of people who live, the number of people who lived in the location last period. So, kind of in this model, remember U bar and A bar are exogenous. So those are not going to be the sort of the source of in our explanation here for historically driven agglomerations or path dependence. But P and lambda and history itself directly through lagged L in the same location will be. And all of those forces of history get stronger, the stronger are the agglomeration parameters alpha and beta. so the second result that we found useful for thinking about models like this is a notion of persistence. So this is not yet anything to do with path dependence. This is still to do with the dynamics of the truly dynamic equilibria in the model. So this proposition, tries in a sense to convey, without linearizing around a steady state or anything like that, a notion of speeds of convergence. So we can define a variable mu as kind of like across all locations, the max change in the variable. So if I'm defining mu L, then I'm talking about the max change in the L's across all locations relative to the min change in the L's across all locations. So when mu is high, that means that this system is bouncing around a lot. The max location is changing a lot and the min location is changing very little. So that this 3x3 system of equations summarizes those mu variables for L and W and pi. And it summarizes how mu is today relative to how mu was yesterday, last period. And what this this sort of sandwich form matrix in the middle says is that whenever this matrix A tilde, which is directly related to the matrix A I showed you earlier, whenever that thing approaches 1, this I minus the matrix to inverted is of course going to grow without bound. And so that means that the bound that you can place between sort of changes in the past and changes today will grow and grow and grow, which is to say that as we get closer, remember, as alpha and 1 and beta 1, as they grow, those are governing stronger and stronger spillovers. As they grow, the speed of this system is kind of slowing down. That's what this is saying. And so to put that in words, this is a notion of, this is again a slice through that sufficient condition at common parameter values. And it's saying that, as if alpha and beta 1 and beta 1 were low, this is going to be a very fast moving system. But as alpha 1 and beta 1 grow to the boundary of the point where we know there might be multiplicity, the system really slows down. And that's what's being shown here in this kind of heat map sense. Okay, so the final thing to say is about genuine path dependence. And to talk about that, we need to talk about steady states. So we're going to, a steady state will just be a resting point for the dynamic system you saw earlier. That's here. That is to say, where all endogenous variables are constant over time. That's the definition of a steady state. Obviously, to even talk about that, we need to have the exogenous things to stop moving. So those are just going to be held at some arbitrary but fixed constant value as well. So that's the definition of a steady state. This is a proposition about when you know that there will be unique steady states. And so Proposition 3a gives us a condition for when there'll be unique steady states. And if you're following along, you'll notice that it looks a lot like the condition for a unique equilibrium. The condition for a unique equilibrium, is to remind you, is written up here. It's about the spectral radius of the A matrix evaluated at values of spillovers that are contemporaneous, alpha 1 and beta 1. The condition for a unique steady state, however, is much more demanding. It's going to require that that exact same matrix is not evaluated at the contemporaneous alpha, but at the sum of the contemporaneous and the historical alphas, and likewise the sum of the contemporaneous and the historical betas. So now we need to have a unique steady state, not just unique equilibria. We need the sum of both modern spillovers and historical spillovers to be small enough that this spectral radius is lower than 1. So that, that to me was instructive. It sort of said that, you could have a well-behaved dynamic model where equilibria are unique. That is to say, alpha 1 and beta 1 are sufficiently low. Yet you could still have interesting real-world plausibly phenomena like path dependence and multiplicity of steady states, like I was alluding to earlier, if alpha 2 and beta 2 are high enough that they take the sum of the spillovers across the threshold and into the region where this uniqueness condition fails. Okay, so just to stress, that's a sufficient condition. It's not, a necessary and sufficient condition. Of course, it would be impossible, to imagine such a condition that is true as we stated it for any geography, right? However, you know, that we would point out that this is, in a sense, the weakest condition that you can state, the weakest sufficient condition that you can state that would be true for any geography. That is to say, if it's violated, as stated here, then you know you can always find arbitrarily many geographies, a continuum of geographies that do definitely have multiple steady states. So it's kind of the weakest possible sufficient condition. Okay, so anyway, the implication of all this is that path dependence in this kind of setting can be easy to study. It can exist and be easy to study. In high dimensional complicated dynamic models without linearizing around steady states and approximating anything, we can have unique equilibria and yet still have multiple steady states, and hence talk about path dependence. This is a numerical example that illustrates some of that. This is an example without any spillovers at all. So 3 locations. This is the simplex of where the adults live. Remember, the sum of the adults is fixed, so they're all going to live somewhere. So we can illustrate them on a 2-dimensional plane. At a symmetric world, symmetric locations with no spillovers at all, no surprise, there is a unique steady state, and it is in the middle. It's a symmetric, that's the only unique steady state, stable steady state. However, if I crank up these spillovers, in particular, if I crank up the alpha 2, then there's going to come a point where that middle point is no longer a steady state, and it already happens here. You can maybe see it better if I crank it up even further. Now these kind of arrows are leading away from the middle. That is, if we were to start anywhere near the middle, the dynamics of the system would take you away from that. Where to? Well, to one of 3 possible steady states that would involve almost all the people living in one location or another or another. There are also, of course, unstable steady states too, but there are 3 stable steady states. So we have a setting with unique equilibria, yet multiple steady states, just like I kind of alluded to, because the spillovers are high enough that can happen. Finally, we can talk about asymmetric locations. So if there was one location that was just better, here location number 1 is like San Diego, it's just really nice there, then no surprise, with no spillovers, the unique stable steady state is no longer in the middle. It's kind of biased towards being near San Diego. That is to say, sorry, it's not, there are 3 locations here. This is not a smooth plane of space but it's biased in the sense of the mass of people. There's more excess mass in San Diego than in, let's say, Boston or Chicago. But as we crank up spillovers, again, the same types of things can happen. So here's high spillover setting where there are, again, 3 stable steady states in the 3 corners where, if we're lucky, we end up in a steady state where everyone does live in San Diego. But if we're unlucky, we live in a steady state where everyone lives in Chicago or, God forbid, Boston, Claire, and that would that can happen, of course, in this model, despite the fact that one location is better than the others in terms of fundamentals. Okay, so again, this is the sort of basin of attraction around one of the bad steady states. If we were to start anywhere in there, we would end up in this bad steady state. Okay, so this is a numerical setting, very easy to work with, in which the kind of phenomena of path dependence that I referred to earlier can happen. All right, so the final thing we can talk about here is a notion of good and bad steady states numerically. I'm not going to have time to go into this, but the paper talks about a bounding result. So you can talk about a notion of aggregate welfare, which we call omega. It's kind of almost like a bit of a behind the veil of ignorance kind of notion of alpha. Of welfare. And we can talk about like a good vector of initial conditions that ends up in a steady state, in which welfare is high, and a bad initial vector. And so we can sort of rank the starting points. And this proposition, it's a little messy, but let me just advertise it. It's a bounding result. It says how big or small can the difference in the best welfare steady state and the worst welfare steady state, how big can that difference be as a function only of parameters? So even though it's in these multiple steady state systems, it's very hard to find them all on your computer, in a 10,000 dimensional system, but you could apply this kind of bound result to say, well, if I live in a world where the trade costs are of a certain shape, then it's very likely that if there are multiple steady states, they are very different in terms of welfare and things like that. If we live in a world in which the fundamentals, the productivities and amenities are very dispersed, then these bounds get bigger. Okay, so I don't have time to discuss those details much, I'm sorry, but let me just try to now tell you about some numbers that we put on this model. So to do that, we're using US data, as I already mentioned. Part of the appeal of the US data is the existence of a long swathe of nice micro-location data from the US Census. So starting in 1800, we know where, there are proxies for where people lived in sort of spatial units, which are going to be kind of US counties, basically. And then we're going to sort of take 50-year time steps beginning in 1850 for all the other variables of the model. These are going to be variables that are available from the US Census. So why 50 years? Well, no good answer there, but to say that, in a model where all you have is kind of adults and children, we did want it to be easy to sort of go to the data and look at people we call adults. Those are going to be people above the age of 20, and expect them to live for sort of roughly, one lifetime, one time period in the model as an adult. So we sort of thought 50 was roughly a guess as to sort of the average lifetime between, say, 20 and 70. And we didn't want overlapping time periods because that's not impossible to handle in this model, but it would add an additional complication. Finally, I'd say this is obviously a model without forward-looking agents, and so it's to me there's some appeal of appealing to a myopic model like this when the time period is sufficiently long. I don't think it's crazy to imagine that that people behave myopically when it comes to 50-year time steps. Okay, so the variables we need are really just L, the population in each location, and W, the kind of nominal earnings per person in each location. And we extract those two things from the census. We also extract other things in years where it's possible, like bilateral migration flows and bilateral trade flows. The trade flows come from the standard CFS source. Those two data ingredients are not necessarily needed every year. What is needed every year is population and earnings. And so we get those from the census as best as is possible. Okay, so to estimate the parameters of this model, the estimation is not completely trivial because of the possible multiple equilibria at parameter values, the certain possibility of multiple steady states at various parameter values. So we sort of had to design a procedure that would be robust to those possibilities. The procedure is also designed to be relatively easy to explain because it follows a sort of three-step process. I don't have time to do all the details here, I'm sorry, but the first step in a sense is only necessary because we don't know what those migration and trade cost parameters are. So we're going to sort of project those things on distance and then estimate their distance slope in the usual gravity kind of way. So, for example, for trade flows, the distance slope will be 1. We already knew that, roughly 1. And for migration, it's going to be somewhere between 1 and 2 in our data as well. But, in some sense, the only role of step 1 is to get data on tau and mu. Step 2 is then kind of going to do a model inversion that relies on knowledge of tau and mu in order to kind of convert from a space of the model in terms of unobservables to a space involving observables on which we have data and we can run simple regressions. And then step 3 will be those simple regressions. So again, I'm sorry I have to go fast, but these are the migration and trade flow gravity regressions, just the flow on distance with the usual gravity fixed effects. Again, trade slope of roughly -1. Migration, we did it for each time period, and it's always in the ballpark of kind of between -1.5 and -2. So we, in our preferred estimate, we just pool those 4 years and just assume it's constant over time. It turns out not to matter much. Step 2 involves this inversion. I'm sorry, I don't have to do the details, but I don't have time to go into the details, but the goal is to kind of transform from data that we do have, which is really just data on incomes and the where the people are, the L's, into these other variables, which are going to be kind of the prices of goods at the origin, little p, the prices of goods at the destination, the price index I already talked about, and then the analogous things for the migration flows as well, but in welfare terms. Okay, so there's a result that says that inversion is unique, as you would hope there would be. And then finally, we arrive at this estimating system of equations that's very standard actually in the urban literature, but just with one kind of augmented difference. So it's a locational labor supply and demand system of equations, just like a Rosen-Roback kind of empirical framework that you may have seen before. The first one is a demand equation. The second one is a supply equation. The only difference is that, remember, this is a model where locations make different products. And migration is costly and involves sort of utility differentiation across space. So to recover the usual Rosen-Roback framework, all you have to do is set the product differentiation and the migration taste differentiation to infinity, and you'll recover the canonical case. There's a parameter we want to know, which is sort of, how do your wages depend in the demand equation on the local density today, that's alpha 1, and on the local density in the past, that's alpha 2. Likewise, how much does the wage today in the labor supply equation depend on people today, that's beta 1, and people in the past, that's beta 2. Now, of course, if sigma and theta are not infinity, you also have to control for these shifters, these endogenous shifters, the price indices of goods and migration. And you have to have data on those things, which was the whole point of the step 2 inversion, was to kind of get the data on those things. All right, so you need instruments, just like the usual supply demand equation economists know well, just like the Rosen-Roback tradition. But the model kind of suggests a type of instrument you would look for. Very naturally in the demand equation, the error term involves productivity. In the supply equation, the error term involves amenities. So that suggests that a good shifter, a good instrument, an excludable instrument in the demand equation would involve an amenity shifter, and vice versa in the supply equation. And that's the kind of thing we try to develop. So in the demand equation, we appealed to the emergence of technologies like air conditioning that changed over time the amenity value of things like maximum temperatures. High temperatures used to be a bad thing, and then over the long swathe of US history, they no longer became such a bad thing. Maybe they even became a good thing. On the instruments for the supply curve case, we appeal to kind of technological changes in agriculture that basically change the suitability of soil types and topography types for certain crops over time. We're using the sort of change in suitability in a potential yields FAO framework by each location as the suitability changes from sort of old technologies and old seed types to modern technologies and modern seed types. So we're always including kind of locational fixed effects in all of this. So all the identification is coming off of changes in amenities or changes in productivities. Okay, so column 2 is our preferred set of estimates here. Column 1 is where I'll admit, somewhat heroically tried to estimate not only the spillovers, but also the sigma. I've never seen this done successfully anywhere in the literature before, and we didn't succeed either. You're really sort of, it's a very heroic attempt to try to estimate sigma this way, I think. And so in column 2, we just punt on that and say, let's just calibrate sigma to a value that's common in the literature, in the trade elasticity literature of 5. And then what you get for alpha 1 and alpha 2 is in this range here. That is to say positive. So there are sort of positive productivity spillovers, not just contemporaneously as has been documented before, but also historically. And so that kind of column is going to be our baseline in what follows. Likewise, for the amenity one, we can try to estimate theta and sigma, but the estimates are kind of all over the place and have huge standard errors on everything. A very good sign of poor identification. No big surprise there. So in column 4, we just calibrate to values of sigma and theta that have been prominent in prior work, and these are going to be our baseline here. We, in the paper, discuss robustness across all the other columns that are shown here that are different calibrated values of sigma and theta, but for the results I'm about to show you, we'll use column 4. Okay, so just to put a picture on what this looks like in the end, these are where those parameter values end up in terms of that uniqueness and steadies of the equilibrium and the steady state that you saw earlier. The dynamic path is thankfully in the region of uniqueness. That means we have unique equilibria, but the steady state parameters, remember the sum of the spillovers, is in this region here, which allows the possibility of multiple steady states. Okay, so I'm gonna just skip that. So the final thing I want to talk about is some counterfactuals that you can do at those parameter values. So I don't know how to do this. We thought about this for a long time, but we thought it would be fun to sort of try to quantify the benefit of the role of a location having kind of quote unquote good history in terms of its long run success. So to take an example, we're gonna, to be precise, we're gonna pair up every pair of county locations in our data of 5,000 county locations. So one example of a pair is Milwaukee and New Orleans. We're going to construct pairs based on the closest 1900 population that they have. And then we're going to swap their A bars, that is their productivity, their exogenous productivities in 1900 alone. So an example, Milwaukee and New Orleans had the same populations in 1900, basically. They're kind of population buddies, but we're going to swap randomly across lots of simulations, sometimes swap and sometimes not. The swapping or not is going to be drawn randomly. And sometimes, in a sense, give New Orleans the lucky advantage that Milwaukee actually had in 1900. Everything else will be held constant. So A bar and U bar throughout time will be held constant with the exception of this one swap. So we think of these as pretty small perturbations around the factual path that the US economy took in this model relative with some counterfactuals that just do these kind of nearest population neighbor buddy kind of swaps. And the results are kind of crazy. So here are just some randomly chosen examples of what can happen. So in 1850, everything's identical because we haven't shocked anything yet. 1900, the actual history shown in the top left can diverge from the 3 alternative histories. These are just 3 of our simulations. Here's 1950, here's 2000. You can see that all chaos is broken loose here in just 3 simulations. Just as a result of these seemingly innocuous kind of buddy swaps, you can end up with extremely different outcomes, even fully 100 years later. And so some of the outcomes look relatively like the reality, and some of them kind of don't. And these were just 3 randomly chosen ones. So to put a finer point on that, you can look at this in a more aggregate sense, not just 3 simulations, but now we'll show you kind of all 200 that we've run so far. Maybe the most interesting finding is down here. This is showing for each location in terms of its factual population in 2000, the spread of its counterfactual 200 simulated populations in 2000 across our 200 simulations. And you can kind of see whether you're a big location or a small location, you can have a massive change in your population even after 100 years in this model, even as a result of these very small initial condition changes in 1900. And actually, to our surprise, these things are not slowing down. The effect of these perturbations in 1900 is not slowing down. It's, if anything, growing. That is to say, the correlation between your location's population in reality in 1900 and across 200 simulations in 1900 is 0.8 in 1900. So, chaos hasn't fully set in here, but it's only 0.5 after 100 years by the year 2000. So, this kind of chaos, this lack of ability to predict is growing actually over the simulated time. These are the locations that kind of, in a sense, were lucky. and by the reality of history, as opposed to our 200 counterfactual swap histories. Maybe no surprise, coastal and Great Lakes regions have been the beneficiaries of agglomerated economic history. They're the ones in red in this picture, where most of the simulations offered them a 2000 welfare that was worse than their actual realized 2000 welfare. The final thing to say is that, of course, welfare has a tendency to be less spread out. This is what I think Don Davis was alluding to earlier in Jim Rauch's kind of phrase: does history matter when it only, does it matter only when it matters little? So there is a tendency for historical shocks to have a big implication for population values, but less so for welfare, because of course welfare smooths out over space. People can move and people can buy goods from other locations. So people can arbitrage away spatial welfare gaps through goods and migration markets. But this figure shows that the spread of welfare across locations in 2000 can still be enormous. So the elasticity across locations of their 2000 welfare with respect to their 1900 productivity shock that they received, has a mean across our simulations and across our locations of 0.2. So, that's to say that a 100-year-old productivity shock can have an elasticity of 0.2 with respect to your welfare today in this model, even though welfare differences get arbitraged away across space. So, to summarize, this model says that, 100 years is a very short amount of time in a model like this. Small initial condition changes can have large and even growing effects even only 100 years later in a model like this. As it happens, those 200 simulations, we've let them run forever, and they do all eventually converge back to the same steady state. So this is not a setting where the shocks that we've fed in, small shocks, lead to path dependence, but they lead to a kind of form of persistence that's incredibly long-lived, and and it is kind of de facto path dependence, a la proposition 2 that we started with. Okay, so I'll stop there, and as I promised, here are some good examples of textbooks where you can go to learn about all the work being done in this space, and from real first principles in a way that I haven't, of course, had time to do justice to. Thanks.
Thank you very much, Dave, for such a terrific lecture. So in the interest of time, we will not ask all of the excellent questions that there are here in the box, but as a reassurance to all the participants, we will be sending all of these to Dave, of course. And luckily, the question with lots of upvotes here on the Ralph question you already addressed, so that's terrific. Thanks very much. I will hand over to Daniel for information next.
Dave, thank you very much. Fantastic lecture, fantastic work, pushing the frontiers in this area. It's been great to see you all, and I hope to see you again next week for our next lecture. The material for Veronica is just going up on our website, so you'll have the reading list and abstract to prepare yourself for next week's lecture in a few moments. Thank you very much, and good night from London.